Hello students, in this video lecture I am going to discuss the of associativity of the join operation. Join operation is this, and meet operation, which is this, in a lattice L. We have already discussed what we mean by the join, and the join is denoted like this, V, and we have already discussed what we mean by meet operation, which is denoted by inverted V, and also we know what is a lattice. All these concepts have been discussed in separate videos, in my earlier videos. So if one is interested in knowing more about these operations, then one can just refer to those videos. But speaking briefly, we have that in a lattice is a special type of PO set or a partially ordered set in which join and meet are defined. And as far as the join and the meet operations are concerned, if you are taking join of two elements A and B, this means that you are talking of the least upper bound of A and B, or you are talking of the supremum of A and B. So provided it exists, and in a lattice this operation is well defined, which means that you can talk of the join or the least upper bound or supremum of any two elements in a lattice. And then when you talk of meet of any two elements in a lattice, if A and B are elements of a lattice, then the meet means the meet is the greatest lower bound of the two elements A and B, or this is the infimum of A and B, provided this greatest lower bound or infimum, this it's one and the same, provided this exists. And in a lattice, which is a special type of PO sets, these exist, which means that meet is a well defined operation in a lattice. So we are in a lattice L, and we just have to show that these operations of join and meet are associative in the lattice L. So the result which we are going to discuss in this video is that if L is a lattice, if L is a lattice, then if L is a lattice and if L is a lattice and A, B, and C are any elements belonging to L, then the join is an associative operation and the meet is an associative operation, which means that the first thing that we have is that A join B join C is same as A join B join C. That is, join is a associative operation, which means that you can put the brackets anywhere. Instead of putting the brackets here, you can just change the order of the brackets and you can put the brackets over here. And a parallel result we have for meet, that A meet B meet C is same as A meet B meet C, which means that meet is an associative operation, which means that instead of putting the brackets here, if there are three elements, and instead of putting the brackets here, you can change the order of the brackets, which means that I can put the brackets over here with A and B. So this is true for any A, B, and C belonging to L, where A, B, and C are arbitrary elements of L. Now, what we are going to do for proving this result is that we are going to prove the first result in detail, and the second one will follow, which means the second part will follow by using the duality principle, because we know that by duality principle, if a statement is true in PO sets, in all the PO sets, then in all the PO sets in consideration, in context, then we have the dual of it will also be true in all the PO sets, which means now as far as this particular statement is concerned, if we prove that this particular statement is true, then the dual of it, how will the dual of the statement be obtained? The dual of the statement will be obtained by replacing these join symbols by meet symbols. So if you replace this by this join by meet, this join by meet, this join by this meet, and this join by this meet, and so by duality, this is the dual statement. This statement is the dual of the upper one. The lower one is the dual of the upper one, and if this one is proved true by duality principle, this one is also proved true. So we are going to concentrate on this one, and we are going to prove this one. The second part, the first part we are going to prove in detail. The second part automatically follows by using the duality principle. So what I am going to show is that A join B join C is same as A join B, A join B, A join B join C. You can speak like that because there is a bracket over here. So A join B join C is same as A join B join C. So that is what we are going to prove first. So now we have to show that A join B join C is same as A join B join C. This is what we have to show. Now we know that the join operation stands for the supremum. So we can write, in other words, that we have to show that supremum of this element and this element, which is itself supremum of B and C, because join stands for supremum. So B join C is same as supremum of B and C. So supremum of A and this element, which is itself supremum of B and C, we have to show that this left hand side is equal to the right hand side, where what is right hand side? Right hand side is A join B join C, which means it is supremum of this expression and this element, which means that this is supremum of the first expression, and the first expression itself is supremum, because A join B is same as supremum of A and B. So we have to show that the right hand side is actually the right hand side is supremum of this expression A join B, which is supremum of A and B, and C. We have to show that the left hand side is equal to the right hand side. So this is the left hand side, this is the right hand side, where this join operation stands for supremum, and this join operation stands for supremum, but the supremum, this is the join of these two expressions, and this expression itself uh, is a join expression, which means that it is supremum of B and C, and this expression again is itself a join expression, which is the supremum of A and B. So you have to show that left hand side is same as right hand side. Now this is equivalent to showing whenever you have to show that we are in a lattice, we have to remember that we are in a lattice L, and a lattice is a PO set. And in a PO set, all the three properties hold: reflexivity, antisymmetry, and transitivity. Now, antisymmetry says that if X and Y are two elements in a PO set, although L is a lattice, we are in a lattice, but a lattice can be viewed as a PO set. So, if you take X and Y to be two elements or expressions or elements in L, and if you have that X is less than equal to Y and Y is less than equal to X, then these two expressions would together imply X is equal to Y. This means that if we have to show that two elements are equal, X and Y, then you just have to show that X is less than equal to Y and Y is less than equal to X. So now we are in a lattice, and the lattice L can be viewed as a PO set, and in this PO set, or in this lattice especially, you have to show that this left hand side is equal to the right hand side. Now, in order to show that left hand side is equal to the right hand side, it is equivalent to showing that we show that left hand side is less than equal to right hand side, and the right hand side is less than equal to left hand side. Because if we are able to show these two things, that the left hand side is less than equal to the right hand side, and right hand side is less than equal to left hand side, by antisymmetry, left hand side will become equal to right hand side. So what we show, if we call this as LHS, left hand side, and if we call this as RHS, right hand side, then we just have to show that the left hand side is less than equal to the right hand side, and the right hand side is less than equal to the left hand side. This is what we have to show, because if we show these two things, then automatically by antisymmetry, left hand side will be equal to the right hand side. So let me concentrate on this one first. I will show that left hand side is less than equal to right hand side. So I just try to show this part, that the left hand side is less than equal to right hand side, and this is how I proceed. Now just concentrate on the left hand side. The left hand side is supremum. So now supremum of A and supremum of BC, this is the left hand side. This of course is greater than equal to A. Why? Or in other words, we can say that A is less than equal to supremum of A and supremum of BC. Why? Because supremum of uh, A and supremum of BC is the supremum of these two. It is the supremum of A and it is the supremum of B. Supremum is the least upper bound, which means that this particular expression, which let's say I'm calling as X, then X is the supremum of A and this, and supremum is the least upper bound. So X is the least upper bound of these two. Because X is the least upper bound, it's an upper bound, which means that this X is greater than equal to these two elements, or in other words, you can say that these two elements are less than equal to X. So by that argument, A comes out to be less than equal to X, which is A is less than equal to supremum of A and supremum of A and supremum of BC. And again, by the same reason, you have this expression, supremum of BC is also less than equal to supremum of A and supremum of BC, which we are calling as X, just to refer to it. So just so that it becomes easy to refer to it. So these two expressions, or these two elements, are less than equal to x, because this expression x is the supremum or the least upper bound, or therefore it's an upper bound, and therefore these two elements are less than this upper bound, supremum of A and supremum of BC, or we are calling it as x. So these two elements are less than equal to x. So now these two expressions we mark this as 1, we mark this as 2. And also, as far as supremum of BC is concerned, because supremum of BC is supremum of both B and C, or it is supremum of B and C, means least upper bound of B and C, or an upper bound, or because least upper bound is itself an upper bound. So supremum of BC is an upper bound of both B and C. Therefore, supremum of BC has to be greater than equal to both B and C, or B and C have to be less than equal to supremum of BC. So in any case, B is less than equal to this. So this is what we have. And again, for the same argument, C is also less than equal to this. So we have C is less than equal to supremum of this. I'm writing as it is. This expression I'm writing as it is. So C is less than equal to supremum of BC, is less than equal to supremum of A and supremum of BC. This is what we have. And now this one I'm marking as 3. So as far as this particular expression is concerned, which I had called as x, we can see that if we just take 1 and 2, then from 1 and 2, from 1 and 2, from 1 and 2, we get that this x which we are using to denote this supremum, that is, this x is an upper bound of both A and B. So we have that supremum of A and supremum of BC, which we are calling as x, so that it becomes easy to refer to it. This particular element is an upper bound, is an upper bound of both A and B. And because it is an upper bound of both A and B, like from 1 and 2, because it's an upper bound of both A and B, this means that this implies that supremum of AB, which because this is an upper bound, so so this is so the least upper bound of these two has to be less than this, because this is just an upper bound. And if you take the least upper bound of A and B, the least upper bound of A and B is the supremum of A and B. And this least upper bound is lesser than any other upper bound of A and B, and this is any other upper bound of A and B. So this supremum of A and B, which is the least upper bound of A and B, is definitely less than equal to this x, which is just an upper bound, not the least upper bound. The least upper bound is lesser than any other upper bound, and this is any other upper bound. So supremum of A and B, which is the least upper bound, is lesser than this upper bound of A and B, which is supremum of A and supremum of this BC. This is something which we were calling as x, and I mark this as 4. So we have just shown in 4 that supremum of AB is less than equal to supremum of A, comma supremum BC, which we had referred to as x, so that it becomes easy to refer to this expression. So this was marked as 4 on the previous page, and I have written this again. And 3 also we found out, which I have written again because it's on the previous page. And 3 gave us a relation that C is less than equal to supremum BC is less than equal to supremum A, comma supremum BC, which again we had referred to as x. So just taking 3 and 4 together, so 3 and 4 together imply, so what is the conclusion that we are getting from 3 and 4? 3 and 4 give that this expression x is acting like an upper bound for both C and supremum AB. So this together give that this x is this x is nothing but it is this expression supremum A, supremum BC, which we are referring to as x. This we are calling as x in this proof. This is an upper bound. This is an upper bound of both. This is an upper bound of both C and this. It is an upper bound of both C and supremum AB. Which means what? Which means that this whole thing is because it is acting like an upper bound of these two. So if you take the least upper bound of C and this, the least upper bound of C and supremum AB will be lesser than this, because this is just any other upper bound, and the least upper bound is the least of all upper bounds, so it has to be lesser than any other upper bound. This is any other upper bound of C and supremum AB. So if you take the least upper bound of C and supremum AB, which means that if I take the least upper bound of C and supremum AB, means that if I take the supremum of C and supremum of AB, this is the least upper bound of C and supremum AB. This is the least upper bound of these two. This has to be lesser than equal to this supremum of A, supremum of BC. It has to be lesser than equal to this. So because of the same reason which I have just said, which I'm going to repeat, because this comes out to be an upper bound of these two, but this is just an upper bound. But if you take the least upper bound of these two, which means that if I take the supremum of these two, then supremum of these two has to be definitely less than equal to this, because the supremum is the least upper bound, so it is lesser than any other upper bound, so it has to be less than this, which is any other upper bound. So this is one expression that we have, which is one thing that we get over here. And what is that? What is that you had to show? You had to show this, the that this expression, the left hand side is less than equal to the right hand side, and the right hand side is less than equal to the left hand side. So if you take a look at what we have got supremum of C, supremum of C and AB, supremum of C and AB, supremum of C and AB, supremum of C and AB. This is the right hand side, supremum of C and supremum of AB, supremum of this. This is the this is one thing that we have got. Supremum of C and supremum of AB is less than equal to supremum of A and supremum of BC. Supremum of A and supremum of BC. So which means that I have shown that right hand side is less than equal to left hand side. I'm marking this as star. So star gives that the right hand side, I can mark this whole expression. This whole expression you can mark as something. I can call this as let's say capital A. So star gives that the right hand side is less than equal to left hand side. Right hand side of A is less than equal to left hand side of A. I'm marking this whole thing as A. So we have shown that the right hand side is less than equal to left hand side. Now we have to show that the left hand side is less than equal to the right hand side. So what is the next thing that you have to show? The next thing that you have to show is we have to show that the left hand side, this is the left hand side. We have to show that the left hand side of A, left hand side of expression A is less than equal to the right hand side of A. Now what is the left hand side? Left hand side, as I said, is this, or we have to show that this supremum of A, supremum BC, this I have to show less than equal to supremum of uh, supremum of supremum of C and supremum of AB. So let me write on the next page what I have already shown. This is something which I have already shown, which is star, and this is something which I have to show. So let me just write down what I have already shown and what I have to show and compare the two. So now this is what we have shown. We have already shown that the right hand side of A is the expression that we had to show. Basically, A is the associativity part that we had to show, that A join B join C is same as A join B join C. That is supremum of A and supremum of BC is equal to supremum of AB and C. This we had called as A, and we have already shown that the right hand side of A is less than equal to the left hand side. So this is what we have shown. I have written it again over here, and this we had marked as star. So we have already shown that the right hand side of A is less than equal to the left hand side of A. What we have to show is the opposite. That is, I have to show that the left hand side of A, which is this, that is supremum of A and supremum of BC, is less than equal to the right hand side of A, which is this, that is supremum of AB and C. Now if you compare this is something which we have to show. If you compare this with the expression which we have already shown, if I write this expression in another way, I write it as supremum, so that there is a match between the two. So because the firstly the supremum term comes, so I'll write the supremum term first. And this is supremum of, because B is coming later on in this supremum term, so B I will write later on. So I write supremum of CB, comma A. I have to show that this is less than equal to supremum, and here the term which is coming is supremum term comes later on, so I'll keep the supremum term later on. I'll write C first, and then in the supremum term B comes first and C later on, so I'll write B first and then A later on. So if this is what you have to show. Now if you compare this particular expression which we have to show with what we have already shown, that is star. Now, if you just compare, you can see that this expression is this expression which we have to show is mostly similar to what we have shown already. The only difference is that supremum, 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 instead of A, you have to show this result for C, and B is as it is. Then instead of C, you have A, and then supremum, supremum, instead of A, you have C. So here also there is a difference. Instead of C, you have A. And then supremum, supremum, B is as it is. And then instead of C, you have A. The only difference we can see that in star and star dash, if I mark this as star dash, let's say, the only difference in star and star dash that we see is that there is a difference of A and C. Wherever A is written, that is replaced by C. Wherever C is written, that is replaced by A. So wherever A is written, that is replaced by C, and wherever C is written, that is replaced by A. So this is the only difference. So which means that star dash actually immediately follows from star, because the only difference between star and star dash is that wherever A is written in star, in place of A, C is written, and wherever C is written in star, A is written. So this means that you can obtain from star you can obtain star dash directly by interchanging the roles of A and C in star. So if you interchange the roles of A and C in star, which means that wherever A is written, just replace it by C, and wherever C is written, just replace it by A. The result immediately, the star dash immediately follows. So, and in fact, because A, B, and C belonging to L were arbitrary. So if we replace A altogether in star by C, and if we replace C altogether by A in star, there would be no harm in that, because A, B, and C are arbitrary elements of L. So this is just a notation that we are writing. So instead of A, we can write C, and instead of C, we can write A. So just making those replacements, replacing A by C and C by A, then A by C and C by A, we get star dash, which means that this is nothing but the left hand side of A, and this is nothing but the right hand side of A. So this means that we have shown that left hand side of A is less than equal to right hand side of A, and we had already shown that right hand side of A is less than equal to left hand side of A. So because right hand side is less than equal to left hand side, and left hand side is less than equal to right hand side, therefore by using anti-symmetry in L, because L is although a lattice, but it can be viewed as a PO set. So using anti-symmetry in the lattice L, we have that the left hand side of A is equal to the right hand side of A. So therefore we get that star and star dash together imply, star and star dash together give that the left hand side is equal of A is equal to the right hand side of A, which means that supremum of A, supremum of BC, this is equal to supremum of AB and C, or supremum can be replaced by join. So A join, this supremum again can be replaced by join of B and C. So this is A join B join C. This is equal to A join B join C. So which is the associativity in with respect to join in the lattice L. So therefore you have that this operation, the join operation B or join operation, this is associative in L. This operation is associative in L. Now, one thing which I want to mention over here is that although this star dash, we have written that it follows from star. Here you can write a line that now star dash, here this we had shown that star dash, now star dash follows from star. star dash follows from star by interchanging by interchanging by interchanging the roles of, or let me write over here, by interchanging by interchanging the roles of A and C in star. So, and thus we get star and star dash together give this. Now here we have obtained star dash just by interchanging the roles of A and C in star. But if you want to prove independently, if you want to prove star dash the way we had proved star, that can also be done rather than saying that star dash follows from star by interchanging the roles of A and C. We can independently prove star dash also. Why? By just moving in the same way, the way we did for star. In order to prove star, which shows that right hand side is less than equal to left hand side, what we did, we started with the left hand side, which means that we started with this. We started with the supremum of A and the supremum of BC, and then we said that A is less than equal to supremum A, supremum BC. If you can just recall, this is what we did. I just want to show you that we can move in the same way. This is what we did. This was the first step when we were proving star. We started with the left hand side, this one. We started with this left hand side, which is this, and then we just using the definition of supremum, that supremum is the least upper bound of both these elements. We took that A is less than equal to this, and then again, because this is also less than equal to this, because this is supremum of these two, we said that B is less than equal to, because this is supremum of B and C, so B is less than equal to this, and so finally B is less than equal to this also. And also then we just wrote that C is less than equal to supremum of BC. So we can proceed in the same way. The only thing is that when you start with the left hand side, then you get that the right hand side is less than equal to the left hand side. So again, when you have to show that left hand side is less than equal to the right hand side, this is what you have. When you have to show that this is less than equal to this, then you start with this. Now when, if you want to show independently, if you want to show star dash, now this is also same as star dash only. The only thing is that this is also same as star dash. The only thing is that these two um, expressions, the one which is at the top, this one, and the one which is at the bottom, they are written differently, but they are just the same. So if you have to show this star dash, then the you have to exactly proceed in the same way. Here, when you have to show that this particular expression is less than equal to this, you started with this and you proceeded in the same way. You proceeded in this way. This is the way. Now when you have to show that this is less than equal to this, again you will start with this expression, and then you will proceed in the same way. And the moment you start with supremum of A, B, and C, then you will write that C is less than equal to supremum A, B, and C. And then instead of A, you will write C when you start with this. And then again, here again, instead of supremum B, C, it will be supremum A, B. And then again, instead of C over here, it'll be it'll be A. So you will find that the whole proof will exactly be the same. The whatever we did for proving star, everything will be the same. The only thing is that you have to start with this expression. When you start with this expression, then this will come out to be less than equal to this, and you will find that in the proof, wherever for proving star we have written A, you will find that you have to write C, and wherever you have written C, you have to write A. That is the only difference. So star dash can be proved independently also, and or we can just say a line that star dash follows from star by interchanging the roles of A and C in star. So both the ways are actually okay. So in any case, we have shown that join operation is associative in L. So which proves part one. So that was part one, and part two, which was about the meet operation being associative, which was that A meet B meet C is equal to A meet B meet C. This is what had to be shown, and I told you that this part follows from this only. This part follows from part one. Why? By using the duality principle. By using the duality principle, since this expression is true, the dual of this expression, which is this, will also be true. because the dual is obtained by replacing all the joins by meets. So by duality principle, when a statement is true, then when a statement is true in all the PO sets, then the dual of it is also true. So from this follows from this follows from part one using duality principle. So you don't have to actually prove it separately, but again we can prove this separately also by the same argument. The only thing is that if you start with here, what we have done in this proof is that we started with proving this, and we use the definition of supremum. But if you are and then using duality principle, we got this part 2. But if you start the other way around, which means that if I start with part 2 first, the only thing is that because meet is the infimum, the meet of any two elements. If you are taking A meet B, then A meet B is the infimum of A and B. This is the infimum of A and B, or this is the this is the greatest lower bound of A and B. So, if you are using part 2 first, then you have to use the definition of infimum or the greatest lower bound. But the arguments have to be given in the similar way, but you have to use the definition of infimum and or greatest lower bound, and using the arguments that are required for the infimum and greatest lower bound, again you can obtain this in a similar manner, not exactly the same, because there we had supremum, here you have infimum. So definitely there is a change in the proof, but you can proceed by starting with part 2 first, and then once part 2 is proved, part 1 is automatically shown by again by using the duality principle. So this is all about associativity of join and meet in a lattice.